Today I'm going to talk about some of the research that, that I've been working on called the statistics of dirty data. It's basically, long story short, we've been looking at using statistical tools and reconciling that with traditional database guarantees of integrity, currency, privacy, things that were generally logical constraints in the past. And I'm sort of going to start off with some of the theory and then talk about how we're actually building those into practical systems. So many of you in this room are familiar with data science. This is obviously the data science track. Many of you, if you pulled out your business card, would have data scientist as your job role under your name. So there was an article in the Harvard Business Review a few years ago about the data scientist being the sexiest job of the 21st century. Now, I don't know if I trust Harvard Business Review for knowing what's sexy and what's not, but there was actually something really interesting in this article that I really liked. That the data scientist's role is not purely just statistical, but it is to coax treasure out of messy, unstructured data. This is pretty much what is hard about data science. Data science, in some sense, is the confluence of computation and data. How do we use our programming to basically get our data into a shape that we can analyze? That's basically the gist of what makes data science hard and how data scientists operate in the real world. And if you guys don't know this already, at least this idea of structuring unstructured data is one of the most hot topics in academia right now. If I was to look at the top database conference, SIGMOD, VLDB, and ICDE, since 2012, there have been 204 papers on data cleaning, schema transformation, data integration, data linkage, all under these different names, but roughly speaking, dealing with dirty and unstructured data. And there's an entire industry that has grown out of academia just on this, companies like Trifacta, Data Tamer, and so on. So this is a really hot and growing field, right? And in some sense, the reason that it's a hot and growing field is the database community believes that it has a unique perspective on data cleaning. While many people think about data cleaning as this ad hoc, interactive, unstructured process that is kind of you're freestyling and improvising as things happen, the database community actually has a very precise definition of data cleaning, believe it or not, right? Basically, the way that the database community thinks about dirty data is I have a table that has a well-defined schema. I have a set of integrity constraints on this table. And data cleaning is just the process of constraint satisfaction for a table that violates those integrity constraints. As a concrete example, suppose I have an accounts and billing table, right, where I have employee name, role, and a salary. I have an integrity constraint such as no manager can earn less than an employee. Now, if there is a violation of this constraint, that's called dirty data, and the process of satisfying this constraint is called data cleaning. This is what the database community does. This is the mental model when you talk about data cleaning in a database conference. This is how people think, right? And what the database community has gotten really good at is translating that English statement, no manager can earn less than an employee, turning that into some sort of a logical predicate, turning that into SQL, something that can be executed very efficiently to enumerate all of those tuples that participate in a violation. Now, the hard part is, once you find these violations, what do, right? You could make an employee a manager. You could set her salary higher or lower, right? Many different choices. That's what makes data cleaning hard. So I argue that this model is in some sense stuck in the 1980s. This model is stuck in an era when the primary use case of data cleaning and data integrity and integrity constraints was accounts and billings, transactions, and things like that. But nowadays, we interact with data in a fundamentally different way. Data is, in some sense, data in and of itself is not the product. We're often using it to facilitate predictive models in the future, analytics, visualizations. In some sense, we're programming with the data. It's not that the data is the end product, right? And that's basically the premise of the work that we've been looking at over the last 5 years at UC Berkeley. Basically saying that how do we revisit this idea of data cleaning? The database community has a very strict notion of what data cleaning is and what it isn't. How do we revisit it in the era of these kinds of new statistical analysis? In some sense, everything we're doing is an aggregate. Every single data point isn't as important as it was before, and perhaps there are new ways of approaching problems, new analyses that we can bring to bear on these problems. So the TLDR of this talk is that the formalism of the old times is good. We should be thinking about data cleaning formally. We shouldn't be thinking about this as an ad hoc process. But the theory needs updating. We have lots of new machinery in statistical analysis. Let's see how we can bring this in there. So I'm going to talk about two works. The first work is how do we link the idea of data repair to statistical analysis? In some sense, build a statistical theory about data repair. The second piece of this is how do we use that theory to actually build practical systems that can help you clean data more efficiently. And I'm going to end with sort of what I speculate these things are going to go in the future. So let's start off with a really concrete, motivating example. This is an example that almost every data scientist would immediately associate with. Suppose I have a database such as a list of publications, right? Something like Microsoft Academic Search or DBLP, one of your favorite academic repositories. For each one of these authors, there's a profile page where you can pull out their fields that they've been publishing in and their total number of publications, right? So my advisor is Michael Franklin, and when I pulled up his profile, there's immediately reason to doubt it. He was listed as a database person, but he was also listed as a pharmacology professor. Now, there's clearly something wrong here, right? We obviously know that there were probably 2 Michael Franklins, and the names, there's some sort of a resolution problem between these things. So how do we trust these counts? So that was actually the first 2 weeks of my PhD, was we took this data set, and I went through all 1,350 records by hand, and I actually validated, was this something that the real Michael Franklin wrote? Was this something that the fake Michael Franklin wrote? I actually went through each one of these publications by hand. And turns out, the dirty count is very different from the clean count, right? What happens is there were not only misattributions, there were also things like duplications and things that were not quite publications, things that were double counted in journal submissions, things that were double counted in proceedings, things that were double counted as posters, and so on, right? So the counts are very different. But there is one insight here. Suppose we were interested in an analysis objective. Suppose we were interested in the analysis objective of just ranking these authors. Did I need to clean everything? And the problem with the existing theory on data cleaning was the answer would be yes. When you have a theory of integrity constraints that is based in logic, you only deal with yes or no questions. A database is either consistent or inconsistent. Any query on an inconsistent database is potentially inconsistent. So there is no degrees of accuracy. So the key problem in data cleaning that we realized is that there was no notion of repair to accuracy trade-off. Like this is the piece here that we needed to solve. So we started with a project called Sample and Clean, and here's a citation if you're interested in looking up the paper. That started off with a very simple kind of problem setting. You start off with a SQL aggregate query, such as select count from all the publications grouped by the author. I have a big, dirty database. As a data scientist, you're only allowed to apply whatever data cleaning technique you have to a sample of this data. So you're allowed to devise all of your rules, all of your cleaning, all of your transformation, only on a small sample of this data. Now the question is, how accurately can you answer this query? Now you might think that this is a straightforward sampling statistics problem, right? But the basic problem is that data cleaning actually changes the statistics of the data. And furthermore, dirtiness and corruption can also affect sampling statistics. For example, if I have duplicated records, those duplicates are more likely to show up in any random sample that I have. And in some sense, I don't know that those duplicates are there, because if I knew that they were there, I would have not had this problem in the first place, right? So it creates these chicken and egg problems. So long story short, what ends up happening is, for most of these SQL aggregates, what kind of breaks is the sampling probabilities. And in some sense, the solution method that we had to this problem is coming up with adjustments, figuring out how to do the right bookkeeping for certain classes of data errors and certain classes of data cleaning operations to make sure that these sampling statistics kind of cancel out with each other. And that's basically what we did. This is kind of a gross simplification of the paper, but the basic idea is you can kind of downweight whatever result you have by the duplication probability and estimated duplication probability, and also like whether it is likely relevant to your query and irrelevant to your query. And there's a lot of details in our paper on how we can do that, and there are a lot of tricky proofs, but the point is that what this allows us to do is it allows us to take a sample of data, transform the sample to pretend as if we're sampling from a hypothetical clean data set, reweighting probabilities, readjusting all the weights, dealing with the problems, and now we get a kind of fictitious sample that we can query with any SQL aggregate query. There are a lot of other interesting things that we can do to reduce the variance. We can look at how much does the data cleaning change a certain sample of data, how much does it change a SQL query, what kinds of SQL queries are more sensitive and less sensitive. There's a lot of theory we can build on it just from the simple problem setting, starting off with a SQL query, a sample of clean data, and thinking about how those affect answers. So this was sort of the the genesis of the results that we started thinking about, okay, if this simple problem setting, the simple tie between data cleaning and sampling statistics, even though it was like a very simplified model, started giving us a lot of theoretical insights. For example, in this Microsoft Academic Search result, we realized, given the distribution of data for these 3 authors, we could get away with cleaning only 100 records before, with 85% probability over all possible worlds of those 100 records cleaned, we'd basically get the right answer, right? This is really interesting to us. So in many tasks, it actually suffices to clean a very small amount of data. A small amount of good data goes a long way. So we actually built this into a real system, and I'll give you the links to all the GitHub pages and my website later, where you could basically write a data cleaning program programmatically in our domain-specific language, using crowdsourcing, using machine learning, whatever you wanted, as long as it sort of conformed to our APIs. We would do all the bookkeeping behind the hood to basically estimate and correct for these changes in probabilities, and we integrated it into the Spark stack. So this was a project called Wisteria. There's a paper, and then there's a link probably on my website at the end to the GitHub pages. So I just want to talk about what are the salient pieces here. So we took this work. This was a starting point that was about 5 years ago. Basically, there are 3 pieces. First, there's some notion of uncertainty. We need to think about the data scientists as living in an uncertain world. They get incomplete information about the data that they're working with. They're either working with a sample, maybe it's a noisy view of data, maybe they're seeing dirty data. So they're devising rules, they're devising transformations based on some noisy view of the world. Then there's a language. Data cleaning should almost never be in a Turing-complete language. You shouldn't be thinking about data cleaning as happening in an arbitrary C program. There are well-defined transformations, well-defined data types, and well-defined invariants that need to be satisfied. That was kind of the second piece here. And the third piece was you have some sort of a quantity that you're trying to estimate. Data cleaning is a means to an end. It is not that the data is a product anymore. You're trying to train a model, estimate an aggregate, try to rank something in a list, right? So these were the 3 pieces that we were able to extend several times over the last few years. For example, now what happens if we want to say, how do we most efficiently clean data for a machine learning task? Suppose I've trained a model, and I have a list of mispredictions. I don't know why this model is going wrong. Is it data error? Is it model error? Is it something else? Is it sampling error? Do I just need more data? Do I need to clean some data? Do I need to collect new labels, right? This was the basic question that we had. We took exactly the same machinery as sample clean, and we put it into a system called active clean, where we figured out how to prioritize which records to clean and how to actually update the analysis after cleaning. This turned out to be actually kind of a subtle problem. Talk to me offline if you're interested in this. But long story short, we are actually able to apply this to a lot of interesting real problems. For example, there's a data set published by ProPublica. I don't believe it's online anymore, but it was called the Dollars for Docs data set. It had 250,000 records of medical contributions that were manually labeled as suspicious or not for fraudulent contributions and things like that. The problem is that there were interesting entity resolution problems in drug names and company names. For example, Pfizer has Pfizer Inc. and all sorts of other variants of the same name. They have subsidiaries that all need to be linked together. So now the question is, how much budget if you have a budget of looking at, say, 1,000 of these entities instead of all of the records, how do you most efficiently place that budget? And we basically showed that compared to other techniques, this technique, which we called active clean, performed the best and could actually get very close to the true model accuracy with just a little bit of good data. Again, same thing as sample clean, a little bit of good data with the proper estimation structure, proper reweighting, proper prioritization can actually get you a long way. And basically, there's also a bound for it too. We can basically show that theoretically this is also justified as well. So there are a whole bunch of other applications. I'm just going to kind of breeze through it, but you can replace the sampling with randomization. Suppose instead of seeing a sample of data, the analyst can only see a private view of the data set. That means like some sort of a randomized view of the data set. Again, we can do very similar analysis and say that on a private view of the data set, these are the kinds of operations you can do, these are kind of queries you can answer, and so on. Interestingly enough, the same theory has applications in streaming systems. It has ways that you can actually approximately update views of the data set. Suppose I have a big database of orders, and I have analyst views and analyst visualizations of just the users from the USA, just users with orders above $300, just users from China. And any time that this base data is changed, you're going to have to propagate those updates. Turns out you can pose it as a very similar data cleaning problem where staleness is the type of data error. And you can actually figure out ways to efficiently sample and prioritize your attention in these systems so that you can get boundable query results on these views, but not have to spend the full cost. Again, linking the traditional notion of logical consistency to statistical analytics because you know we're doing some sort of aggregates of the downstream. I'm going to kind of skip through this in the interest of time just so I can get to the exciting stuff. So that was the theory of what we kind of proposed before, right? We wanted to be able to link data repair to some sort of statistical notion. That doesn't help you guys because in some sense that's a really academic model of the world, right? It's sort of thinking about data cleaning in the abstract, not really telling you how to clean your data, but what cleaning is. The next step that we've been looking at is looking at the intersection of data cleaning and program synthesis. How can we leverage new tools in AI to more efficiently synthesize solutions to data cleaning problems? So let's take an example that I've been working on, that I worked on a few years ago. So we sent out a whole bunch of iPads to rural Uganda in collaboration with USAID to collect a lot of data on their reproductive health programs. So they run these training camps in these villages to train young mothers on best neonatal practices and so on. Right? So the key problem here is that when the data came back to Berkeley, it was totally not in the form that we could analyze it. There was a mix of, in the age column, you can see that there's a mix of numerical data and categorical data as well, right? It's like this was partially collected on digital iPads. It was partially collected on paper forms. When it came back, we hired undergrad interns to code this up. This is kind of the familiar problem, right? In all fairness, all the information we need is there in this column, but the problem is it's just not in the format that we need to analyze it. And I see this as kind of symptomatic of what goes wrong in typical data cleaning problems. It's not that the data is completely missing. It's just that the data acquisition and data curation process is divorced from the analysis that you're doing, right? Because if the undergrads were also in charge of analyzing the data, they absolutely would not have typed in 20 when they were entering in the ages. They would have known to convert that into a number, right? Now, what this basically means is something really troubling for people like me who live in the database world. If I was to write, say, a Python program, an R program, to process this data, it would get really long. I would basically have to enumerate all of these small special cases. Every single place where something was done in a unique way, I'd have to write that as one new line in my program, one new transformation rule. And all the scalability that we've been proposing in the database community is pointless if your program is on the order of your data, right? We can scale concise programs. We can't scale a program that's the same length of your data, right? That's kind of hard. So this is what we really found that happened is like the math section of your programming, of your code was really small, but the data cleaning section was huge because it would just have all of these transformation rules. So there has to be a better way. There has to be some way into avoiding your program from encoding these literals that are representing these errors. But then this goes back to the old database perspective, right? In the old database perspective, when you think about things in terms of integrity constraints, no manager can earn less than an employee. You're saying something really deep here. You're really saying, I want my data set to satisfy these properties, right? Can we leverage this idea of integrity constraints to basically come up with a new programming model for data cleaning? That's kind of our next project that we've been looking at. What I want to be able to do in a data set like this is to be able to say, I want this age to be a floating point number. I want this property to be satisfied. These are the kinds of operations you're allowed to do. You're allowed to delete tokens. You're allowed to translate text into numbers. I'm going to put in a question mark because I don't care about what the literal you are. You figure out how to do that. You put both these pieces, the invariant and the language, into an optimizer. The optimizer turns away. I don't care how much money or how much compute you burn on this, but then generate the program for me. Now, from a human's perspective, you only have to care about specifying the template and specifying the invariant. You don't have to care about how the optimizer is choosing to execute it, how the optimizer is choosing to group functions together to make these more efficient, how the optimizer is choosing to implement these functions underneath the hood. This is ultimately what we want. And to get it there, we realize that actually something has changed in the last few years. data cleaning is actually, in this, the way that I present it is an instance of planning, as you see in AI and machine learning today. Basically, you have a language of transformations. You have some notion of data quality. You have some sort of a reward, some sort of a quality, the number of invariant violations that you have. And your output is a composite transformation. That means a composition of these things, a sequence of these transformations, if you will, that optimizes the reward cumulatively over the entire data set. And the cool part is that we've actually gotten tools, more tools in recent years to solve this than we've had in the past. We have, first, a lot more compute. We can parallelize and scale these things up. And second, we've gotten a lot more understanding on how to actually address these high branching factor search problems. So our idea was that something like this has definitely been thought of before, but it may have been dismissed 10 years ago as an impractical solution to something like data cleaning or data transformation. Can we revisit this problem with the new tools that AI has to offer? And that's basically our system. It's kind of cutely known as AlphaClean. Basically, it has a 3-layer stack. At the top, there's an execution engine that basically takes in that spits out a logical program and generalizes literals in your system. At the bottom, there's a specification layer where the human only specifies a library, basically says these are the functions you're allowed to use, specifies a quality function, what defines clean, and then there's some sort of things that handles hints on data types and things like that. Then there's a narrow waist in the middle, this optimizer, this AI search algorithm that basically searches for the best program that satisfies these invariants. The best searches over the set of transformations that gets you to your invariant solution. So how does this look like in practice? Let's kind of get a concrete example. Suppose I have this data set. I can load this into a pandas data frame. I load this as a standard CSV. I can provide things like patterns. I can say that I want my age to be a floating point number between 18 and 100. I want all the responses from these participants to be alphanumeric. I want all the parishes, the parish names where they collected this data, to be in some code book of dictionary of allowed parishes. Then I can specify multi-column constraints. I can say that I want a functional dependency between parish and date. That means I want there to be a map that means that every parish is associated uniquely with a single day when data was collected. I can also specify more complicated logical checks. For example, I want to make sure that nobody under the age of 22 is listed as having more than 5 children. I can also put in soft constraints, things like I expect age and children to be correlated. I expect that the data kind of looks like the previous year's model. I combine all of these pieces together into a quality function. Our system compiles this down into a single quantitative metric of, per record, a score of how many constraints it's violating. Then the question is, how do we design the language? And we found out that actually most data cleaning fits into a pretty concise language of transformations. Here's a subset of the things that we do, right? For example, find and replace. This is a surprisingly powerful primitive. For a given attribute, find one attribute value and replace it with another attribute value. Clip, that means look at a numerical value and clip it down to some sort of a threshold. Filtering out certain tokens, removing certain weird tokens like substrings from an attribute value, and regexes, right? These are all very well parameterized transformation things, but can actually capture, in composition with each other, can capture a huge set of data cleaning programs. So that basically gives us the first two pieces, right? How do we define a language? How do we define a quality function? And now the cool part is, searching over this is basically a tree search. We basically start off with a no-op, and we start sequencing these things together, right? We start off with a no-op, then we try out a composition with the first transformation, the second transformation, the third transformation. And again, we kind of recurse. We just keep on going forward. Now, as you can imagine, this search space grows exponentially. But there are parts of this problem that we can actually exploit. Typical errors are localized. They often affect only small subsets of the data. And typical errors are systematic. That means they're correlated with certain attribute types. And basically, what this means is that we can actually be very greedy in the search algorithm. And we found that empirically, very greedy search strategies work really well. And the other part that made this possible was we took a leaf out of the Google playbook on AlphaGo. What we can do is we can clean data in small blocks. So we can spend our expensive search on a few small blocks of data and start learning what types of transformations are relevant to this data set. What attributes tend to be dirty, what literals tend to be inside these transformations. And as we keep on going, what this ends up doing is learning a scoring function. If those of you guys are familiar with reinforcement learning, this is actually just a Q function. But what we can do is we can start anticipating what types of transformations there are and encoding domain-specific featureizations to basically make this search algorithm more and more powerful. Like, we can take these transformations, use our NLP techniques to know like what are likely errors, what are likely correlations that we should be exploiting. So in terms of empirical results, we've benchmarked this system against a lot of existing tools. Some of them don't have real names because we don't want to call out commercial tools and so on. But for example, we looked at a data set of news articles. These were news articles about terrorist incidents since the 1970s. And these articles often had duplicates because there were multiple news articles that referred to the same incident. They had multiple discrepancies in like the dates that they happened in. It had lots of missing values and so on. So we came up with an entity matching tool, which will be unnamed. So a tool that does deduplication of data, so it does large-scale deduplication. A tool from MIT that does outlier detection, just numerical outlier detection. And then a classical database integrity constraint satisfaction algorithm as was used back in the day in your IBM systems and so on. So now if we took these three things, EM-only, deboost, and chase, and combine them together naively, we're going to get some precision and recall, and we're obviously going to get the best precision and recall of all of them because we tuned these really well. But the cool part is alpha clean, AC plus L alpha clean, and this learned heuristic actually does better than the combined algorithm because what we can do is we can actually turn all of those objectives into a single quality function and optimize jointly over them rather than treating them as individual systems, because we put this in this AI planning framework where we can basically optimize over all of them simultaneously. Now, obviously, that's at the cost of a lot more compute. It requires 8 times more compute than the competitors. Fair enough, but that's kind of where the research has to go. We believe that there are interesting opportunities as thinking about these problems as combined problems, thinking about them as program synthesis problems, rather than building specialized systems. Similarly, the benefits are seen in problems like schema integration. Suppose I have to do 2 steps. I have to integrate a schema. That means I have 2 data sets, which their columns align, but they align in some weird way, and I don't know what that is. So I first have to join the columns, and then I have to merge the data and deal with any errors. Again, you could do these 2 things separately. You can do schema integration and your data cleaning in two different passes. But doing them as a combined operation has benefits because it optimizes these things jointly. Sometimes there's going to be an order of operations here. So let me sort of move into here. So the last result that I'd kind of like to sort of highlight over here is there's something really interesting going on here, right? Alpha clean, we believe, changes the way that you think about data cleaning because it's talking about data cleaning as a search over the space of data cleaning programs, rather than searching over the space of data edits to a certain database. Right? And the cool part about this is actually one of our recent insights was this means that everything we know about machine learning actually starts applying to data cleaning. There is a notion of overfitting, underfitting in data cleaning as well, right? Some transformations that are overly specific may not generalize to new data. They're just not going to be relevant. They won't apply to any new data that comes in, right, if it's extremely specific. Transformations that are too general might have unwanted side effects on new data. And we can actually exactly characterize that in the same way that we have statistical learning theory to characterize the way that prediction rules may overfit, underfit, and generalize. We can talk about data cleaning programs overfitting, underfitting, and generalizing. Turns out we can get a really elegant formula that says that this is roughly proportional to something called a sensitivity, which is how sensitive is your data quality function. That means if one record was to change, how much would the change in, how many new violations would you create? Times 1 over square root of the amount of data, which is your standard sampling problem, and roughly logarithmic in the size of the number of transformations you're searching over. So if you're searching over more transformations, you're more likely to overfit. If you are more sensitive, you're not likely to generalize. If you have more data, it solves both problems. So it's kind of very similar in spirit to the kinds of things that we're seeing in machine learning. But we can characterize this for data cleaning if we pose the data cleaning problem in this way. So that sort of ties up these 2 pieces. We had sample clean, which was linking data repair to statistical analysis, and alpha clean, which is applying these new AI machinery to talk about data cleaning. And the consequence is it kind of goes full circle. We can actually start analyzing the output programs with alpha clean from a statistical perspective as well, building up a rich theory that we've now developed in machine learning and bringing that over to the idea of data transformation. To me personally, if we start talking about data cleaning as being 80 versus 20 in terms of the amount of effort that you're putting, it's kind of a travesty that we don't have a statistical theory to describe data cleaning. And this is kind of a first step in that direction. We should be doing a lot more, understanding how these kinds of operations affect any downstream processes that go on. So here are some of the references. My website is listed below, and there are links to code. There's probably links to my GitHub as well. But we've basically done a whole bunch of different work, and all of them kind of have the same flavor. We're talking about data cleaning before statistical analysis. I've done work on crowdsourcing because data cleaning is often very intimately linked to having humans come in and verify and clean data. And we've also talked about how do we write to approximate databases, which also has the same kind of feel to it. And if there's one thing that I want you to take away from this is data cleaning is a statistical problem. We should not analyze these two problems in a divorced way. We should be analyzing data cleaning and whatever analysis you're doing in a joint way, because this is where bugs come from, by treating these as two distinct processes. Thank you.
We have time for a couple of questions while we get the next speaker set up.
Yeah.
Nice work. I like how you kind of link it into the same general field as approximate database.
Yeah.
Not exactly the same as approximate database. I had a question about how people write constraints. So most of them were obvious.
Yeah.
But the one where nobody under 22 has more than 5 children, that seemed a bit arbitrary. I have a feeling there's some kind of, it seemed a bit arbitrary, that constraint. I have a feeling it was a hack.
Yep.
What could you do to help people write constraints?
Good, yeah. Great questions. So the way that I look at it is this is always the problem with declarative programming in general, right? It's declarative until it's not, right? You start having to encode some imperative things inside your declarative programs. So what we are working on right now is rather than having users write these constraints specifically, have the users transform a few example records. When they have difficulty coming up with a certain constraint, show on a few records, actually manually modify this and try to infer out what kind of constraints that what is the most explainable constraint that they're trying to enforce by their modifications. This is one solution to the problem. I think it's a really hard problem, and I think it's a problem. If there was a good solution to it, there would be a good solution to synthesizing SQL queries. There'd be a good solution to synthesizing data log queries. This is a huge problem. It's like, why do we sometimes tell our Postgres optimizer hints to do joins better? It's exactly the same problem. It's like it should work, but it doesn't. So, yep. Yeah, no, it's a great question.
I was wondering if you just quickly clarify one of the aspects of
Yeah.
what you were talking about. You showed this black box optimizer.
Yeah.
And then you also showed the user specifying some transformation functions. Is the optimizer generating transformation functions, or is the user responsible for every transformation?
So the user specifies templates. That means transformation functions and a free literal, if you will. The optimizer automatically generates the space of possible transformations, the space of possible sequences of transformations, and optimizes over that.
Okay, and then the user says, like, I want this transformation function, I don't want that transformation function.
Yeah, or the user's quality function prunes the space. The optimizer prunes the space using the user's quality function. Yeah, what the user's defining as clean. So.